Starting with a new module. That is challenges in multi-carrier communication, MCM. Challenges in multi-carrier communication. We'll first talk about PAPR, which is known as peak to average power ratio. Peak to average power ratio, peak power divided by the average power. And we'll see how this comes into picture, how can we avoid it, different methods to reduce the PAPR. Are we able to completely reduce PAPR? Do we lose something by doing it? And things like that. So first let us discuss how this PAPR comes into picture, why it is regarded as a challenge for multi-carrier communication or OFDM in particular. First of all, let me go to this block diagram of OFDM transmitter and receiver. So here you have a transmitter receiver system, and first you have the mapper, which is the incoming data bits. They are mapped onto modulation symbols based on some type of modulation, and then an IFFT is performed. Then you have this parallel data converted into serial. Cyclic prefix is added. It goes to a digital to discrete to analog converter, and it gets multiplied with a carrier frequency Fc, goes to the power amplifier, and then the signal gets transmitted out, and that signal is being received by the receiver. Of course, after linear convolution with the channel impulse response, the signal gets received by the receiver, then it is down converted to the baseband. These analog values are converted to discrete values by an ADC. Cyclic prefix is removed. Then this serial data is converted to parallel. After the performing FFT, we get the frequency domain signals back, the modulated symbols, and then we have to do the demodulation. In order to get back the signals, a demodulation has to be performed, and we get the data bits at the output of the receiver. So this is the basic block diagram of FFT based OFDM transmitter and receiver. And let us see how this problem of PAPR comes into picture. We are talking about PAPR, peak to average power ratio. So here from this point till this point, you have your discrete signal. Your signals are discrete in nature. After the DAC, discrete to analog converter, you have the signal converted back to the analog form, and this analog signal that is a function of continuous time, is analog till this point, and here you have a analog to discrete converter which converts it, and the rest of the processes they are discrete in nature. Here you have analog processes happening, and here you have discrete processes happening. So you can see most of the computation is happening in the discrete section, and but you also have this analog part of the signal which is very significant, because it is the actual signal that goes to the channel. That is a signal that is being received by the receiver. So your analog part of the signal is also important. Now let me explain this by writing down the equations. So the OFDM signal that comes out here, the OFDM signal which comes out here, which is S of t, OFDM signal that comes there can be written as summation S of t is equal to summation k is equal to 0 to n minus 1, addition of n subcarriers xk, which are modulated symbols, multiplied by e raised to j 2 pi. For the frequency you have, I can simply write fk, which is a frequency. As k varies, the center frequencies of the different subcarriers comes into picture here. It adds into the summation into t. And this fk, which is the center frequency of the subcarrier, fk is equal to fc, which is the carrier frequency here, fc plus k into bn, where bn is the subcarrier bandwidth, that is the separation. So I can further expand this, and I can write it as k equal to 0 to n minus 1 xk into e raised to j 2 pi fc plus k into bn into t. And you can see I can take e raised to j 2 pi fct out of the summation. So it doesn't have this k term. So I can take this term. It can be regarded as a constant here. E raised to j 2 pi fct. I can take it out of the summation, and inside you have k equal to 0 to n minus 1 xk into e raised to j 2 pi k bn into t. All right. So here I have, what I've done is I have separated the carrier part, this part, the carrier part, and this is the baseband OFDM. It is a baseband OFDM. So baseband OFDM, when multiplied with e raised to j 2 pi fct, the carrier, it becomes band pass OFDM. So S of t is band pass. Okay, you have basically an up conversion, converting into a higher frequency band. All right. Now I showed you this equation because it is in continuous time. Usually when we do OFDM, we consider the discrete implementation. Even if you do simulations or even you do problems, we always tend to consider the discrete implementation, which takes care of this part, discrete implementation here up till here, and this part till here. And we assume that rest of the processes, the DACs, the power amplifiers, everything works perfectly. And during the simulation or when we are working on problems, we often consider only this discrete part. But there is something happening in the continuous time. The continuous time, when you convert this discrete signal to analog signal, the actual signal is regenerated there. Okay, actual signal is recovered there. So till here, till this point, you have sample values of the OFDM signal. But from this point, you have the actual time domain signal itself. The time domain, or better, I should say, the recovered signal. The recovered signal from time samples. Now, how are you able to recover the signal? Because you have sampled it in Nyquist rate. So if you get samples, from those samples, we are able to recover the whole signal back. So there is a recovered signal from the time samples. And this signal, it is the actual signal. It is the signal that is resulting from the addition of n subcarriers. Okay, there are total n subcarriers, and this signal that comes here, it is the addition. It is the result of addition of n subcarriers. As a result, what happens? What happens is the different subcarriers, they are all independent with each other. The different subcarriers, they are independent with each other, and these subcarriers, when they add with each other, their phases may coincide. They at some certain points they might be having the same phase, and at certain points they will be having different phases. But there might be some points which have the same phase, and these subcarriers which are having the same phase at a point, they add with each other and result in high peaks. Okay, let me just demonstrate this to you using this expression, this figure. Here you can see four subcarriers: frequency 1, frequency 2, frequency 3, and frequency 4. I've just shown only four subcarriers, and you can see there are certain points like this point where all the four subcarriers, they have the same phase. Okay, here they have the same phase. Subcarriers have the same phase. So what happens is when the subcarriers have the same phase, they add coherently. Add coherently, and they result in this dark colored sum of all subcarriers. They result in high peaks. Okay, they result in high peaks, right? So is there any issue when you have high peaks? Yes, because when you have high peaks in your signal, you have a device called power amplifier here. Okay, that is the device which is kept just before the transmitting antenna. You take any communication system, you will have this power amplifier which is kept just before the transmitting antenna. And this power amplifier, this incoming signal is coming to the power amplifier, and this power amplifier has got a linear region of operation. It has got a certain range of signal values for which this power amplifier will operate linearly. If you exceed the input power to the power amplifier, then this power amplifier will go to a saturation region, and if it goes to the saturation region, what happens is there can be distortions. There will be non-linear distortions, spectral spreading, etc. Certain issues like that. We'll go into detail. Before that, let me just show you the discrete equivalent of this expression. Okay, this expression. This signal S of t, as it goes to this particular channel, and the signal S of t reaches the receiver, of course, S of t, after undergoing a linear convolution with the channel response, it reaches here. It is converted to discrete form, and removal of cyclic prefix, etc., happens. And this signal that you have here at this point after sampling. So ADC is basically doing a sampling operation. From the analog signal, it collects the samples, right? So like if this is the sum is the signal which is analog in nature. The ADC, analog to discrete converter, what it does is it takes the sample values. Okay, it takes the sample values, just like it takes values, a point here, a point here, a point here, a point here, etc. Okay, takes sample values, and these sample values are the sample values which were originally there in the signal at the transmitting end. Okay, and yeah, let me just show you how this analog signal gets converted to the sample values here. So basically I'm going to demonstrate this sampling process, how the sampling process happens here. So there is this signal, okay. I'm not considering the this part here because the carrier gets down converted using this down converter, so I'm not considering this part. I'm only considering this part, the baseband Ofdm section, the section that reaches here to the ADC. So let me denote that section by x of t, and x of t is equal to x of, I'm sampling it. Let me just rewrite this portion again for clarity. I'll just rewrite that portion. I have here summation k equal to 0 to n minus 1 xk e raised to j 2 pi k bn into t. So that is the baseband OFDM part, this part. And I'm doing this is like you can see, this is in continuous time, and I need to perform this sampling operation, and my sampling frequency is sampling time is ts. So you have x of n into ts, where n denotes the number of the different samples, the sample times 0, 1, etc. up to n minus 1. Okay, so n can vary from 0, 1 up to capital N minus 1, and you have summation k is equal to 0 to n minus 1 xk e raised to j 2 pi k bn. Bn is the subcarrier bandwidth, and instead of this t you substitute n into ts. You have n into ts here, and you know that bn is nothing but 1 by tn, and tn, which is the time duration of the whole OFDM signal, it is equal to n into ts. So I can substitute bn as 1 divided by n into ts. So you can have summation k equal to 0 to n minus 1 xk e raised to j 2 pi. For bn I substitute 1 divided by n into ts. You have n into, have a k here, n into ts. So ts and ts get cancelled, and we have summation k equal to 0 to n minus 1 xk e raised to j 2 pi k n divided by n, and this is the discrete OFDM, sampled OFDM that you get after this process ADC. So before ADC you have the signal like this, x of t. After ADC you will have x of n, as I denoted before. All right. Basically, addition of subcarriers. Let me come back to the PAPR part. Addition of subcarriers. Sometimes certain subcarriers, they might come at the same phase at a particular time, and they result in high peaks. And this high peaks, it may drive this power amplifier into a non-linear region of operation, because all power amplifiers, they have a region of operation where they operate linearly in the sense the output is linear to the input, or you can express it as y of t is equal to some gain of the amplifier into x of t. That's a linear signal. And this power amplifier has got a region of operation, a range of input power for which this the output is linear. If the input signal exceeds a particular power, if the input signal to the power amplifier exceeds a particular power, which we call the saturation power, PSAT, saturation power, this power amplifier will move to a non-linear region of operation, and as a result signal distortions can happen, non-linear distortions, spectral spreading, all these things can happen. Okay, so this diagram, it shows the characteristic of a power amplifier. In the x-axis you have input power in decibels, in the y-axis you have output power in decibels. Input power is the input to the power amplifier, output power is the amplified amplified input, that is the output power. So you can see there is a region of operation where the relationship between input and output is linear, and that is called the linear region. Okay, we want the power amplifier to work in this linear region. Okay, we want the power amplifier to give maximum output. What happens is if the input say, so you can see a point here, okay, which is marked as ideal operating point. And beyond that point the characteristics shifts to non-linear. So if it was linear, it should have followed this dotted line, but after this ideal operating point, the output of the power amplifier, it becomes non-linear. And you can see from this range, from around 0 to 10 input dB input power, the output output has very less change, and beyond a certain point the output almost remains a constant, which means it reflects a non-linear region of operation. Okay, and for that what we can do is we can define a term called IBO. IBO stands for input back off. Input back off. IBO stands for input back off, which is IBO is equal to the expression for IBO is 10. IBO is usually expressed in decibels, dB. So IBO is 10 log to the base 10 P saturation divided by P average, where P saturation is the saturation power of the power amplifier. P sat is the saturation power of the PA power amplifier. P average is the average power of the signal. It is the average power of the signal. So what we want is we want the power amplifier to work in this linear region. And what is the significance of this quantity IBO? So this ratio, the ratio between the saturation power of power amplifier and the average power of signal, it is expressed by this quantity IBO, and this expression IBO can this logarithm can be expanded as P sat of in dB decibels minus P average in dB. In decibels, it is the difference between the saturation power and the average power of the signal. Sometimes what happens is the power of the signal, if it goes beyond this saturation region, this power amplifier goes into a non-linear region of operation. So for that signal, what we can do is we can reduce the input power of the signal. We can reduce the input power of the signal by a factor IBO such that even if it has high peaks, even for your maximum value of the signal, it doesn't cross this ideal operating point. Okay, so the idea is you have the saturation power here. Saturation power is the maximum power with which the power amplifier can operate in a linear way, in a linear region. And we can make the input, we can reduce the input power of the signal by a factor of IBO. If you can reduce like that, then the average power of the signal becomes here. Average power of the signal comes here. Average power of the signal reduces. And if you have IBO equal to PAPR, if you have IBO equal to PAP, peak to average power ratio, peak power divided by average power, even for peaks, it doesn't exceed this ideal operating point. Right? So that is a small description about the characteristic of power amplifier. So remember, power amplifier has got a linear region of operation, and we want the power amplifier to work in that linear region of operation. Otherwise, what happens is we will have distortions in the signal, which are again non-linear in characteristic, and that may lead to spectral spreading, out of band radiation, in band radiation, a lot of problems, spectral widening, non-linear distortion, noise, etc., etc. And it's a widely researched area. A lot of methods have been found to reduce PAPR. Let us take one by one. There are mainly two types of power characteristics for a power amplifier. This is called SSPA. SSPA stands for solid state power amplifier. There are also another characteristic called TWTA, which I won't be taking now. This diagram is good enough to understand the idea of PAPR. So if you have high peaks like this, if you have high peaks, we need to reduce it. Otherwise, this will lead to the nonlinear operation of power amplifier, this component power amplifier. So how can you reduce it? So when you reduce the power of this whole signal, one disadvantage that is going to happen is your signal might have your lower amplitude values operating at this area, which is having lesser gain, which is having lesser output power. Okay, here you can see the output power is less when compared to this. And so how can you reduce PAPR effectively without significantly affecting the signal? If you simply reduce the peak power, then proportionally your whole power of the signal is going to reduce and your output power is going to be less. So how can you prevent this thing? For that, let me just write down the expression for PAPR. We haven't, so peak to average power ratio. So there are peaks happening here like this. There are peaks happening. PAPR is defined as ratio of maximum instantaneous power. It is a ratio of maximum instantaneous power to average power. Okay, PAPR of Ofdm signal x of t. Okay, PAPR of Ofdm signal x of t is the ratio of maximum instantaneous power to average power of x of t. Equation PAPR of x of n can be written as maximum of magnitude x of n square. So you have x of n as amplitude. When you take the square, it becomes power divided by expectation operator, which means I'm taking the average of x of n square. Average of power, that is expectation of magnitude x of n square. Maximum x of n square divided by expectation of x of n square. And this n can vary from 0 to n minus 1, which means I'm taking all the n samples. I'm taking and considering n samples, capital N samples, and I'm finding the sample which has got the maximum power. I'm finding the sample which has got the maximum power, and that is going to be this value. Okay, if I take this example, this sample value here, the sample value that I've marked here, it is having the maximum value, and that value will come here divided by average of power of all sample values, average power of all the sample values. So when I do like this, I have the maximum value of power, the sample with the maximum value of power here in the numerator, that is the peak value, and in the denominator I have the average value of the power of all the samples. So it is a peak to average power ratio, or PAPR. And when you have high peaks like this, what happens is the output of power amplifier goes to non-linear region of operation, and that results in the high PAPR results in nonlinear distortions and spectral spreading or spectral widening. Spectral spreading means the power of one subcarrier getting on to the power of the other subcarrier or interfering with the neighboring subcarriers. It can also be interpreted as intercarrier interference, power of one subcarrier interfering with the nearby subcarrier. All right. So you have this issue of PAPR, and I hope the idea is clear for you. How PAPR, what is the reason for PAPR? How PAPR can be measured? PAPR can be measured using this equation, where it is simply the peak power divided by the average power. And when you measure it like this, if you consider n minus 1 samples, another issue happens. And this issue is that you consider only capital N points. You have only N points. But in reality, you may have signal peaks which are having more amplitude than this. And I think from this figure, it is very clear that you considered samples which are equally spaced, but the maximum amplitude of the signal actually lies here. But that sample point is not part of the sample point which I have. I have n sample points which are spaced apart by a sampling time Ts, and I don't have this sample point here which is having the maximum amplitude. According to Nyquist rate, I need only n sample points. In those sample points, this point is not considered. This peak value is not considered. In that case, how will I know? So I would feel like this is my peak value, the value which is having maximum amplitude, and I might define an IBO. I might define an IBO based on that value, such that the average signal value is here and the peak can come up to here. But in reality, I have another point here which is having more power than the point which I have taken, the sample points which I have taken for Ofdm. In that case, what will I do? I also want an idea about the points which are in between. I need to consider some more points here. If I consider some more points, then this point, high peak point, also will get considered, which means I need to reduce the sampling time. I need to reduce this sampling time, let's say by a factor j. So you missed out this point because the sampling time was more. Let's say that I have a reduced sampling time, Ts divided by j. Okay, earlier it was Ts and now the sampling time has reduced, Ts divided by j. So that you have more number of samples now, your sampling time has reduced. Earlier you had n samples and now you are going to have j into n samples, right? You are going to have j into n samples because in Ts the sampling time has got reduced by a factor j. So your number of samples is going to increase by a factor j. And you have more sample points now. You have j into n sample points now. And this j is called the oversampling factor. Oversampling factor. Which means you are sampling the signal at a rate greater than the Nyquist rate. So you have an oversampling factor j. And let us see how it affects the signal. So I simply want more number of samples. So I'm reducing this number of reducing the sampling time. Let us do the same sampling process again, but now with a reduced sampling time. So let me try the sampling. Okay. Now what I'm going to do is oversampling by a factor j. I'm trying oversampling by a factor j. So instead of x of t, I will have now x of let me rewrite again for clarity. Sigma k equal to 0 to n minus 1 xk e raised to j 2 pi k bn into t. And now I'm oversampling by a factor j, which means I will have x of instead of t, I will have n into ts by j, that is equal to k equal to 0 to n minus 1 xk e raised to j 2 pi k bn. For t, I can now substitute ts n into ts divided by j, n into ts divided by j. And I do the same substitution. I can substitute bn summation k equal to 0 to n minus 1 xk e raised to j 2 pi k. bn is 1 divided by n into ts, n into ts divided by j gets cancelled, and you have summation k equal to 0 to n minus 1. So addition of n subcarriers xk into e raised to j 2 pi kn divided by n into j. But now the value of n, it goes from 0 to jn minus 1. Okay, the value of n. You have n number of samples. So x of n, I can write it as x of n. Yeah. So I have jn values, which means n varies from 0 to jn minus 1. All right. So oversampling is a method which is used to have an accurate PAPR value. For accurate PAPR value, you need to oversample the signal. And ideally, how much oversampling is required? If you want to completely if you want to get the correct idea of PAPR, this oversampling factor must be infinity, right? Then you have all the points. If I have oversampling factors infinity, this sampling time will goes to 0. If the sampling time goes to 0, it means that the samples are so close to each other, which means they actually give you the analog signal as such. but that is not practical. We cannot have hardwares which does oversampling by a factor of infinity. So in practice we take oversampling factor as j is equal to 4. So in practice j is taken as 4, or sampling factor is taken as 4. In most of the research papers you can see that j is taken as j equal to 4 gives you a fairly good approximation of the PAPR, peak to average power ratio value. Okay, now finally let me also tell you about this function called CCDF. CCDF stands for complementary cumulative distribution function. In research, to represent the PAPR, to illustrate the PAPR of Ofdm signals, often this parameter called CCDF, complementary cumulative distribution function, is used. And this CCDF is a very useful parameter in characterizing the amount of PAPR, and CCDF of PAPR of a signal x of t is equal to probability that PAPR of x of t is greater than a threshold value. So probability that this signal x of t, the PAPR of x of t, is greater than a threshold value. So that is this function CCDF. So this del is happening here in this x-axis, different values 0 to 4 up to 12, and on the y-axis you can see the CCDF function, which is nothing but the probability. CCDF is basically the probability. So if I consider this point, this dark line, solid line, correspond to n equal to 16. So n equal to the 16 subcarriers. So when you have 16 subcarriers, the probability that this signal value, the PAPR, is greater than threshold value 4. So let me just take down here. Yeah. Okay. Or for better clarity, I'll take some other point. Let me take a point here. Yeah, 10. Okay. The corresponding point I have here is somewhere between 10 raised to minus 3 and 10 raised to 4. Okay, close to 10 raised to minus 3. So at this point, probability that PAPR will be greater than 10 is somewhere close to 10 raised to minus 3. But if I take n equal to 256, which is this line, the same value of 10, 10 is a threshold value, the probability that the PAPR goes greater than 10 is even more. Okay, somewhere here it is greater than 10 raised to minus 3, right? Again, if I take n equal to 256, the probability that PAPR is greater than 10 is somewhere here, close to 10 raised to minus 2. It is even more than the previous case, which means as the number of subcarriers increases, the probability that PAPR is greater than a particular threshold value is getting bigger. That is very obvious. If you have more number of subcarriers, more number of sinusoids gets added, and the PAPR is going to increase. The peak value is going to increase. So CCDF plots shows you how the PAPR varies for a particular threshold value. And you take any threshold value here, you can see that as the number of subcarriers increases, the probability that PAPR is going to be greater than a particular value, or in other words, the CCDF of PAPR increases. So this function, complementary cumulative distribution functions, is a useful tool to characterize the PAPR of an Ofdm signal. With that, I'll end the class for today.